Multi-conceptual questions are favorite for any competitive examination. In this video, I'm going to discuss 5 interesting, important, challenging, tricky, multi-conceptual questions for the topic differential calculus. Earlier, I put up a video where one question was discussed, and due to technical glitch, I could not continue with that video. So first watch that video and then continue watching this video. So here is a multi-conceptual question, very important and most favorite expected question. Suppose limit x tends to 0 of fx upon x cube is L, and question says this limit exists where the function is given by this determinant and they are asking minus 112 L value. First thing, I'm going to expand this determinant in order to get the function value. So let us expand this determinant using first row. Observe here, I can see 3 zeros here. So I'm not using properties here. It is better to expand because so many zeros are present. So when you expand using first row, you will get a plus sine x by 2 into this is 0 and this is negative of a plus sine x by 2 square, right? That will be minus of minus plus b cos x, and this is also going to be b square cos square x minus 0. So finally, it is going to be negative of a plus sine x by 2 the whole cube plus b cube into cos cube x. So this is our f of x. So now let us consider this limit as x tends to 0 fx over x cube. Limit x tends to 0 fx value I'm putting from here, that is b cube cos cube x minus a plus sine x by 2 the whole cube divided by x cube. Now let's check the form of this particular limit by substituting x equal to 0 here. So when you substitute x equal to 0 here, the form which you're getting here is b cube minus a cube divided by 0. Now according to the question, that this particular limit is given by L, that means limit exists and limit is finite. So whenever limit is existing and limit is finite, is this form acceptable? See, since the question says limit exists, limit is finite, and here the denominator is 0, so this particular form is not acceptable. What is the acceptable form? If denominator is 0, numerator must be 0 and limit has to be in the 0 by 0 form. If in the question it wasn't given that limit exists and limit is finite, then it was different story. It is saying in the question that limit exists and limit is finite. Therefore, it must be in the 0 by 0 form because denominator is already 0. So numerator must be 0. So from here we conclude this numerator b cube minus a cube must be 0, and therefore a cube must be equals to b cube. So final conclusion here is a is equal to b. So if a equals to b, I can put it over here, and this limit will become limit as x tends to 0. B cube is replaced by a because a is b, so b cube is replaced by a cube. So it is a cube cos cube x minus a plus sine x by 2 the whole cube divided by x cube. Now if you do oral calculation, this will be in 0 by 0 form. Now if the limit is in 0 by 0 form, we can apply L'Hopital's rule, right? So what we do is we differentiate numerator and we differentiate denominator. So here I'll make a space and write the next step. Alright, so I'll write the derivative of numerator. So a cube constant, cos cube derivative will be 3 cos square x into minus sine x. Minus derivative of this term, which is 3 a plus sine x by 2 the whole square into cos x by 2 into 1 by 2 whole divided by 3x square, and that is the derivative of denominator. I can say this 3 getting cancelled everywhere. Now if you check the form of this particular limit, it is 0, right? This will be 0. minus, if you substitute x equal to 0 here, it will be a square, right, by this 2, and denominator will be 0. Now, since again, as I discussed earlier, the limit, this particular limit was finite, right? It was given to be L. So will you accept this form? Answer is no, because denominator is 0. So numerator must be 0, because acceptable form is 0 by 0 form. So this numerator has to be 0. For this numerator has to be 0, that means I can say a square by 2 is 0, and therefore conclusion is a equal to 0. And remember, b is equal to a. So if a is 0, we get b also as 0. So this a value is 0. Now I'll put in the limit. Let me make a space first. Alright, so this here I'll substitute. So limit x tends to 0, fx upon x cube. This limit is here a is 0, so this term is gone. A is 0 here, so this is sine square. Sine square x by 2 cos x by 2 into 1 by 2 divide by x square, right? If I put a equal to 0, so this term is gone. A equal to 0, this will be sine square x by 2 cos x by 2 into 1 by 2, right? Now when x is tending to 0, this will be 1, right? Because cos of 0 is 1. And this 1 by 2 I can shift outside. This minus also I can shift outside. And this will be limit sine square x by 2 divided by x square. And what I can do is I can write down this as whole square. Now if you see this limit, we know the formula limit x tends to 0, sine kx upon x is k. So sine x by 2 upon x, that limit is going to be 1 by 2, the whole square. So final answer is minus 1 by 8. So this limit is coming out to be minus 1 by 8. According to the question, value of this limit was, if you remember, given to be as L. So can I say L equals to minus 1 by 8? A final question was asking about minus 112 into L. So it is going to be minus 112 into L. L is minus 1 by 8. And when you calculate this, it comes out to be 14. The conceptual problem number 3 on differential calculus. एक set दिया है A having elements A, B, C, D, E. Another set is B having elements 1, 2, 3, 4. We are asked to find the total number of onto function defined from set A to B such that important condition FA is not equal to 1. So how many onto functions are possible? So if you say set A, B, C, D, E, it has 5 members, and set B, it has 1, 2, 3, 4 members. If you see the number of elements in the domain is more than the number of elements in codomain, and function has to be onto, that means everyone here will be mapped. So ये तो many one होगा ही, right? It must be many one, right? क्योंकि जैसे A को एक से मैप कर लिया, B को इससे मैप कर लिया, C को इससे मैप कर लिया, D को इससे मैप कर लिया, तो E तो किसी ना किसी के पास जाएगा ही, लेट्स से 2 के पास चला गया, तो बाय डिफॉल्ट ये many one होगा ही, right? So that is first point. An important thing, we have to find out total number of onto function where f is not equal to 1, means A is not mapped to 1. That situation we have to tackle. So for that, what we do is we find out total number of onto mappings first. That will be our step 1. I'm discussing the strategy for solving sums. So total number of onto mappings we are going to find out, and from that we are going to subtract mapping where f of A is equal to 1. So total number of onto mappings minus the mappings where f is 1 will be our required answer. So that is going to be the strategy. So step 1, we are going to find total onto mappings. Step 2, we are going to find mappings in which fa equals to 1. And step 3, you're going to subtract these two to get the required number of onto functions where fa is not equal to 1. Pause this video and listen these statements 2-3 times. Now focus on step 1, that is finding the total number of onto mappings. Look at the situation. We have set A which has A, B, C, D, E, 5 different elements inside, and set B which has 4 different elements. And I have to create onto mappings. That means I have to allot or map these 5 different members to these 4 different members. Remember, the mapping is onto, so everyone must get one mapping, one element mapped. So you can imagine this as 5 different chocolates which you want to distribute among 4 different kids. So this can be done 2 steps. First, what you do, 5 different chocolates you divide into 4 groups. First group will be 1, 1, 1 and 2, right? These are 4 packets. First 5 different chocolates you're going to gift pack in this way. And then each gift pack. So how this division will be done? Total factorial divided by 1 factorial into 1 factorial into 1 factorial. This one has occurred 3 times, so into 3 factorial and 2 factorial for this. So 5 chocolates you're wrapping into 4 groups, and that can be done in these many ways. Now once the division is done, gift packing is done. Now these packets of gift you have to distribute among 4 kids, and that distribution can be done in 4 factorial ways. So total number of onto mappings will be equals to, if you simplify this, that comes out to be 240. We have to discuss case 2 where we have to find total number of mappings when fa is 1, and this is going to be crucial, critical, very very important, sometimes difficult to understand. So I want you to focus on each and every word, listen to every statement carefully and try to feel it, the idea behind it, right? fa is 1, that means 1 is associated with a. If 1 is associated with a, then out of these 4 members which are left here, they are to be mapped to 3 elements, right? So it may happen that out of these 4 members, you know, someone might get associated with 1 also at some given point of time, right? So it may happen that there is a possibility that case 1 is associated to a alone, and remaining these are associated to each other, something like this. That is one possibility. And second possibility is that a, b, c, d, e here, 1, 2, 3, 4 here. Second possibility is 1 is associated to a, and someone else out of these 4 is also associated to 1, and then remaining 3 are associated to remaining 3 normally. So these are 2 different cases, right? I hope you're understanding these 2 different cases. When I say fa is 1, this is one case where 1 is mapped to a alone, and here you have many one situation created among these 4 and 3. And then we have second case where 1 is associated to a, and out of these 4 someone else is associated to 1 also, and remaining 3 are mapped in 1 association. So there will be 2 cases, case 1 and case 2. So let us discuss here case 1, how many ways case 1 can be done. Now when we talk about case 1, 1 is associated to a, that is done. That means remaining are 4 chocolates to be distributed among 3 kids. So first of all, what I do, I divide these 4 chocolates into 3 gift packs. So first gift pack will have 1 chocolate, second gift pack 1 chocolate, third gift pack will have 2 chocolates. Now these are gift packs. Now this division of 4 chocolates, B, C, D, E, into 3 gift packs can be done in 4 factorial divided by 1 factorial for this into 1 factorial for this. Since this is repeated 2 times, therefore 2 factorial for the repetition and 2 factorial for this. So this is the number of ways of dividing these 4 chocolates B, C, D, E into 3 different packets. Once the packets are ready, these three packets will be given to these three kids, three packets to be given to three kids, and that can be done in 3 factorial ways. And when you calculate this, answer I think comes out to be 36. So now let us calculate for case 2. In case 2, 1 is mapped to A, and out of these 4, someone else is also mapped to 1. So what I do first, out of these 4, I pick any one. Out of these 4, I pick any one. Out of these 4, I pick any one and associate it with 1. So that can be done in one way. 4C1 is the number of ways I can pick any one of these, and that once it is picked up, I can associate it with 1 in one way. And then remaining 3, which are the remaining 3? Let's say B is remaining, C is remaining, E is remaining. These 3 are to be mapped to remaining 3. So 3 chocolates to be mapped to 3 kids in 3 factorial ways, and this is your 24 number of ways. So we have found the number of mappings where F is 1, and that comes out to be case 1 36 plus case 2 24. That means 60. There are 60 mappings which are having situation where FA is 1. So what is our final answer? Remember, in the starting of the question we discussed total onto mappings 240 minus the number of mappings where FA is 1. So final answer comes out to be 180. I want you to pause this video from here and watch solution, listen to the solution of this question 4 or 5 times. Very, very important multi-conceptual question, right? It involved PNC also in an interesting way. An incredible question. So next most important and very much expected multi-conceptual question on differential calculus is this number of distinct real roots of this equation. What I call this as function as fx. Let us call this function as f of x. And I want you to observe for this particular function that f of 0 is 1. Very, very important piece of information. We'll be using this later on. Now, I find the derivative, I'll get 4x cubed minus 12x squared plus 24x plus 1. The beauty of this kind of question is, if you try to factorize this, it is difficult. If you try to use trial and hit method to find critical points, is very difficult, right? So sometimes people spend so much time and can't get the critical points. So what is the way out? So notice this point. In this type of question, they purposely give you a polynomial, a biquadratic, which on differentiation results into a cubic polynomial, where it is very difficult to find the critical points using trial and hit or synthetic division method. So what do we do here is, notice carefully, I differentiate this again second time. So when I differentiate this again, this is going to be 12x squared minus 12 2s are 24x plus 24. We can take 12 common. This is x squared minus 2x plus 2. So this is 12 into x squared minus 2x plus 1 plus 1. 2 I'm splitting it as 1 plus 1. So this is 12 into x minus 1 the whole square plus 1. So this is 12 into x minus 1 the whole square plus 12 into 1, that is 12. So if you notice this particular quantity, it is always greater than 0, means positive, right? Because this is a perfect square, that is positive, plus 12, that is always going to be positive, greater than 0. So what is the conclusion? The second derivative is positive. So the second derivative is positive. I want you to understand that f dash x is here strictly increasing. And also notice f dash x is cubic. F dash x is cubic function. So these two are very important, useful information. So if it is strictly increasing, f dash x, and it is cubic polynomial, that means it is definitely going to cut, you know, it is strictly increasing, and it is definitely going to cut x-axis at one place. That means f dash x has exactly one root. If f dash x has exactly one root and the function is strictly increasing, let that root is alpha, let's say alpha is any number. So the sign scheme for f dash x will be plus and minus. And if you imagine the graph of function, this is sign scheme of f dash. So you can imagine the behavior of function f. It will be decreasing here and then it will be increasing. That will be the nature of graph of f. Now let us try to imagine the graph of f. If you remember, f of 0 was minus 1. So at x equal to 0, the function value was minus 1. And alpha is certain number, certain real number, right? Let's say that number is here. Now what is happening? Till alpha, it is function is decreasing and function has to pass through this point. So it will decrease till alpha, and once the alpha is reached, it is going to increase like this. Or you might think like this, alpha may be here, right? So it may something like this till alpha is going to decrease, and after that it's going to increase. So either you consider graph of function f like this or like this. You observe that f cuts x-axis at two distinct points. Either you consider graph like this or like this. In both cases, the graph of function f cuts x-axis at 2 points, and therefore we can say number of distinct real roots of this function is 2. Watch this solution 2-3 times, you will understand, because this is most expected question. Next very important multi-conceptual problem on differential calculus is we have a function f defined from this to this, where fx is given by this formula, g function is defined over this and this, and gx is given by this formula. It says small a indicates the number of points of discontinuity of the function fx, and small b indicates the number of points of non-differentiability of function gx, and there they are asking find a and b. So clearly this question will be done in two parts. In first part we are going to focus on function fx and find out the number of points of discontinuity of this function, and in second part of this problem we are going to purely focus on function gx alone, and we'll find out the number of points of non-differentiability. So part 1 we focus on this function fx, so which is box of x square minus 3. Minus 3 is integer that will come outside the box. Now this particular function here, focus on this particular function x square. This particular function box of x square will be what? It will be discontinuous at those values of x for which this inside quantity x square becomes integer, right? Read this statement 2 times. So x square will become integer, that means x square possible values are what? It can be 0, 1, 2, 3, 4, 5, etc. So whenever x square becomes these integer values, corresponding to that, what is x? Corresponding to that, x will be 0, plus or minus 1, plus or minus root 2, plus or minus root 3, plus or minus 2, plus or minus root 5, etc., etc. Now, whenever x square becomes integer, corresponding to that x values are these. At these values of x, the function will become discontinuous. But hold on. According to the function f definition, the domain is minus 1 by 2 to 2. So minus 1 by 2 to 2. So out of that, I will select only the values 0, then I'll select 1, then I'll select root 2, then I'll select root 3, and then I'll select 2. So these are the points where the function may be discontinuous. These are the potential points, possible points, right? Most likely the function will be discontinuous at these points. Now how to do confirmation out of these? How many points function is discontinuous? The best way is to draw the graph of this function x square. So what is x square function? This is graph of x square function, right? Y equal to x square. This is 0, this is 1, this is 2, this is 3, this is 4, this is 5. At every integer we put a line like this, we put a line like this. At every integer we put a line like this, correct? And then what we do is, at wherever these lines cut this graph, we put a dark circle. We draw the 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 dark circle. Wherever these horizontal line cuts, right? Now you bring it down to this level, right? And then there is a hollow circle. This is the graph. Bring this also down up to this line, right? There's a hollow circle, and this is the graph. This line, let us extend this line up to here, right? Let us extend. Bring this point down, draw the hollow circle. This is the graph. Bring this point down, there's a hollow circle, draw this. Bring this point down, there's a hollow circle. Bring this point down, draw the hollow circle, and this is the graph. Bring this point down, there is a hollow circle, this is the graph. Bring this point down, there is a hollow circle, and draw this graph. Bring this point down, there is a hollow circle, and draw this graph. Bring this point down, and like that you can, if you want, you can draw more graph. So graph of box of x square is these lines, solid lines, these steps. These steps are the graph, right? What is this point? This point is y equal to x square, right? So x equals to 1, right? And here x equal to 2. So y will be y is x square. So whenever x is root 2, then y is 2, right? And like that, this particular point is 2, right? Now you can see the function is discontinuous at 0, it is continuous, right? At 1 you can see it is discontinuous, root 2 it is discontinuous, root 3 it is discontinuous, 2 it is discontinuous. So 0 is a point which was probably very, very crucial. Without graph, we might conclude in a wrong way, right? So drawing graph was very important. From graph I can understand that function is continuous at 0, while it is discontinuous at 1, root 2, root 3, and 2. So a is the number of points of discontinuity. So in this case, a comes out to be 4, because there are now 4 points of discontinuity. Now before I discuss second part of the question, I want you to note down this trick, and this is very, very important, favorite trick for any competitive exam. Suppose you have product of two function gx into hx, and out of that the first function gx is not differentiable at some point x equal to a. And we observe that this particular function, the second function hx, becomes 0, vanishes at x equal to a. So first function is not differentiable at certain point, and the second function vanishes at that point. Then overall this particular function gx into hx will be differentiable at that particular point. Case number 2, the first function of the product gx is not differentiable at x equal to a, while the second function hx at that particular point is non-zero. In this case, the overall function gx into hx will be not differentiable at that point. Very, very powerful and useful. This is our function gx, and remember, for f of x, this function f of x was discontinuous at x equals to 1, root 2, root 3, and 2. Discontinuity implies non-differentiability. That means this particular function is not differentiable at x equals to 1, root 2, root 3. I'm leaving 2 because this function gx is defined at 2 open, right? So I'm discarding this whenever we talk about non-differentiability. So if you look at gx function, it is product of two function. This is one function fx which is not differentiable at x equals to 1, root 2, root 3. And now this is the second function. Let me check value of this second function at x equal to 1, x equal to root 2, x equal to root 3. So let us check, calculate and check. So at x equal to 1, this particular function comes out to be non-zero. At x equal to root 2, when you substitute, the second function of the product is non-zero. Similarly, at x equal to root 3, this second function is non-zero. So the product function, the first the first member of the product function is not differentiable at these 3 points, while the second member of the product function is non-zero at those 3 points. Therefore, it is safe to say gx is not differentiable at x equals to 1, root 2, root 3. Now, I want you to observe gx once again. I'm rewriting gx once again. Now, when you look at this particular gx, now observe from this side, the second member of the product function here. This particular function is not differentiable at x equal to 0. This is not differentiable at x equals to 7 by 4. Now I'll check whether this particular function is value at x equal to 0 and x equal to 7 by 4. So when I want to calculate value of this function at 0 and value of this function at 7 by 4. So let's see, value of function at 0 will be what? That is going to be non-zero, right? And when you calculate value of this function at 7 by 4, that comes out to be 0. You can do the calculation. Now that means this particular function is not differentiable at 0 and differentiable at 7 by 4. So this is not differentiable at x equal to 0, and it is differentiable at x equal to 7 by 4. Please watch that trick again and try to apply this. Trick has to apply it on both sides. First I applied trick from this side, considering the non-differentiability of the first function of the product and checking with the second function. In second case, what I did, I consider this non-differentiability point of the second function of the product and verified with the first function. So it has to be checked both ways. So how many non-differentiability points are there for this function gx? 1, 2, 3, and here one more differentiability point, 4. So number of differentiability points for non-differentiability point for gx comes out to be 4. So b is 4. So overall a plus b value, what was a, if you remember, that was also 4, b is also 4, and final answer is 8. So friends, only this much for this video, and these were very important multi-conceptual questions on differential calculus. I will also be putting a video for multi-conceptual questions or integral calculus, so stay connected with this channel. And by the way, all the best for your upcoming exams. Bye bye and take care.